All right, so in this chapter, I will talk about binomial distribution, Poisson distribution. If we have enough time, I will go over the other parts on uniform distribution, exponential distribution, and normal distributions. Okay. Um, Hello, can you hear me clearly? Can you hear me clearly?
Yes, sir.
Okay. Do you have any problem with my voice? Something? Is this all right?
Yes, I can hear you clearly.
Okay. Now suppose that we have a binary trial in which the random variable can take one of the two value. It could be 1 or 0. 1 with probability P and 0 with probability Q. All right. Then you can find the mean value of Z very easily. What is the mean of Z? The mean of Z is simply 1 times P plus 0 times Q, and you get P. You can also find the mean of Z squared. Okay, and that is 1 squared times P plus 0 times Q, and you still get the same thing, P. And from that, you can get the variance of C, which is the mean of the C squared minus the square of the mean of C, and you get P times Q, where Q is 1 minus P. All right. A binomial random variable is simply the number of successes in n-ability trials. So you can use a binomial distribution to describe the number of successes in n-ability trials. All right. For example, we can use a binomial distribution to describe for the number of defective items among 20 independent items with the defective rate 5%. Okay, so if X is the number of defective items among 20 independent items with that defective rate, then I can say that X follows a binomial distribution. Okay, I use the notation tilde to indicate that X follows that distribution. Okay, and this binomial distribution has two parameters. The first is the number of items that you want to check. So you have 20. And the second parameter is the defective rate. So you get 5%, 0.05. Okay. In the second example, suppose that X is the number of winning tickets among 11 independent lottery tickets with a winning rate 1%. Then X follows a binomial distribution with the first parameter 11, because you have 11 independent tickets. And then you come up with the probability is 1%, so 0.01. All right. For the last example, you get the number of patients reporting symptomatic relief with a specific medication with the effective rate 80%. Then you have X follows a binomial distribution with the two parameters. N is the number of patients, and P is the effective rate 80%. You get 0.8. Okay, is there any questions so far, everybody? Is that clear? Is that all clear? Now let's consider these two examples. Let's consider the following example. The coin is weighted in such a way so that there is 70% chance of getting ahead in any particular toss. Toss the coin in exactly the same way 100 times, and X is the number of heads tossed. Is X a binomial random variable? Yes or no? For A, is that a yes or no? Can you tell me? Is that yes or no? Yes or no? Yes, it is a binomial random variable. How about the second case? A college administrator randomly samples students until he finds 4 that have volunteered to work for a local organization. Suppose that X is the number of students sampled. Is this a binomial random variable or no? Is this a yes or no? Right, it is no. Why? Because for binomial distribution, you fix the number of games you play. Okay, and you count the number of winning games. Am I right? For question B, you fix the number of games you win, and you count the number of games that you have to play to win all the 4 winning games. Okay, so it is another story, completely different. Okay, so in this case, X is not a binomial random variable. All right. Okay. All right. Now I want to talk about the distribution of a binomial random variable. Suppose that X follows a binomial distribution with the two parameters n, p, okay? And you want to find, and then you want to find all the values that X can take. Well, obviously, X could be 0, 1, 2, and then n, okay? It can take those values. The random variable can take those values. And then you want to find the probability mass function, which is the probability that X equals K. How can you get it? How can you get that? In order to get the probability that X equals K, okay, you find the probability that X equals K. First of all, I want to find the probability that X equals N. What is that? The probability that X is N is the probability you win all games. If you win the first game, that chance is P. If you win the second game, that is P. You win the third game, it is also P. And you that you lose. So you lose the first game with the probability Q. You lose the second game with probability Q. You lose the third game with probability Q, and so on. So you get this one, and you get Q to the N. Do you understand what I'm saying? Okay, is that all clear, everybody? All right, what is the probability that X is 1? It is exactly 1. X is 1 if you win exactly one game. So you can win the first game and you lose all the other games. Or you win the second game and you lose the other games, right? You win the first game and you lose the others, so you get all this probability, you get this probability. And then you win the second game, right? But you lose the first game and you lose the others, all the games, correct? Then this sum becomes P times Q to the N minus 1, right? And then you count the number of terms. That would be N choose 1 because there are N games and you want to, and then you pick one game to win, right? And then you get this one. In general, you have the following formula. The probability that X equals K should be N choose K, P to the K, Q to the N minus K. Do you have any questions so far? Is that all clear, everybody? Is that all clear? Okay. All right. Okay. And then you can also find. You can see that now suppose that x1 is 1 if you win the first game and 0 if you lose the first game. X2 is 1 if you win the second game and 0 if you lose the second game. X3 is 1 if you win the third game and 0 if you lose the third game. X4 is 1 if you win the fourth game and 0 if you lose the fourth game. Understand? Then I denote by X the sum X1, X2, and then Xn. Okay? You have this sum. And this sum follows, you see that X is simply the binomial random variable. So X follows a binomial distribution and P. Okay? Is there any question so far? All right, then you can see that the mean of x is the mean of the sum, right? And that is the mean of x1 plus the mean of xn. And each, you know, and then all the xi follows this model, the bullet model. So you get 1 and 0 with probability p and q. Therefore, the mean of xi is p, and the variance of xi is p times q. So I can say that this term here is p. Therefore, the mean of x is simply n times p. For the variance of x, you get the variance of x1 plus xn. And because all the xi are independent, you need that assumption. They are independent. Then you come up with the variance of x1 plus the variance of xn. And each term is p times q, right? So you get p times q. Therefore, this becomes n times p times q. All right? So we come up with the following proposition. Is that clear, everybody? So you come up with the Boltzmann function. You come up with the mean value and the variance. Okay. Let's consider the following example. Then you will learn how to apply the formula in practice. Each sample of water has a 10% chance of containing a particular organic pollutant, assuming that the samples are independent with regard to the presence of the pollutant. Find the probability that in the next 18 samples, exactly 2 contain the pollutant. Can you tell me the answer? Okay, suppose that x is the number of samples that contain the pollutant among 18 samples. Okay. Then X follows a binomial distribution with the parameters 18, and then the probability of getting the pollutant is 10%, so you get 0.1. And you want to find the probability that X is exactly 2. So you come up with 18 choose 2, 0.1 square and 0.9 to the 18 to the 16. Correct? Any questions so far, everybody? And the answer would be on 0.2835. Okay. For the next example, for the question B, you want to find the probability that at least 4 samples contain the pollutants. Question B, that would be the probability that X is at least 4, I think. So you get 1 minus the probability that X is less than or equal to 3. Okay, and then you get 1 minus 18 to 0, 0.1 to 0, 0.9, 18, right? And then you get 18 to 3, 0.1 to the third, and 0.9 to the 15. Okay? Any questions, everybody? And this is what you get. You get the answer 0.098198. Okay? Is that clear? Let's try the next example. A certain battery communication system has a bit error rate of 10%. If 6 bits are transmitted independently, then how many bits on average will be received in error? Then determine the corresponding variance. Okay. Suppose that x is the number of bits received in error, then X follows a binomial distribution with the two parameters on 6 bits, 0.1, because you transmit 6 bits, okay? And then you want to find the mean value, the average value, right? That is n times p, so you get 6 times 0.1, and you get 0.6. For the variance X, you get n times p times q, and that would be 0.5054, all right? That is very straightforward. Okay. Now, let's consider another example. It's a bit harder. Not really hard, but it's not really trivial. Let's think about that a little bit. A certain electronic system contains 10 components. Suppose that the probability that each individual component will fail is 20%, and that the components fail independently of each other. With that, at least one of the components has failed. What is the probability that at least two of them have failed? Okay, so in this case, suppose that X is the number of components that have failed. Okay, then you want to find the probability that at least 2 of the components have failed. So X is greater than or equal to 2. Given that at least 2 of the components has failed, so you want to find the probability that X is at least 2, given that X is at least 1. Okay? Do you understand what I'm saying? Is that all clear, everybody? And then you get conditional probability X is more than 2 over the probability that X is more than 1. Okay? And then you get this probability. Is that all clear, everybody? Okay. And you get 1 minus the probability that X is 0 minus the probability that X is 1 over 1 minus the probability that X equals 0. Okay. Then you come up with 1 minus. And by the way, now what is the distribution of X? In this case, you have 10 components, so X follows a binomial distribution with the two parameters 10 and 20%. So you get 10 to 0, 0 0.20, 0 0.8 to the 10, right? Minus 10 to 1, 0.2 to the first, 0.8 to the ninth, okay? Over 1 minus 10 to 0, 0.20, 0.8 to the 10, okay? Is that all clear to you, everyone? That's good? That's good.
Yes, sir.
Okay. Now we are ready to move to the next distribution, the Poisson distribution. And here are some sample of Poisson distribution. Okay, a Poisson distribution can be used to describe the number of events that you can observe during a period of time. For example, you can use it to describe the number of telephone calls arriving in a system in 1 second, or the number of broad connections to your phone number every day, or the number of photons arriving at a telescope in 1 microsecond, the number of mutations on a strand of DNA per unit length, the number of bacteria on some surface of which in the field, the number of customers arriving at a counter or call center in 10 minutes, and the number of cars arriving at a traffic light in 5 minutes, the number of lawsuits plans occurring in a given period of time. So basically, it can be used to describe the number of events that you can observe during a period of time or within a region. All right. Here is the formal definition of a Poisson distribution. So a Poisson random variable is simply the count of events that occur within an interval. You can get a distributions as a limit of a sequence of binomial distributions. Suppose that Xn follows a binomial distribution with the two parameters n and p such that np equals lambda. So the average, so you don't know the number of trial n or the probability of success p. You don't know that, but you know the average number of successes per time period. Okay, that is the case that we have here. You don't know n and p, but you do know the average number of successes per time period. Then we consider the probability mass function xn equals k, and then you let n go to infinity. You can get the limit, the exponential of minus lambda to the k over k factorial, and we call that that function the probability mass function of a Poisson distribution. So let's say a random variable x is called to be of a Poisson distribution with the parameter lambda if it has the following probability mass function: f of k equals the exponential to the power the exponential of minus lambda times lambda to the k over k factorial. Okay, and then you can find the mean of x by using the definition. The mean of x is simply the sum k times f of k, so you get e to the power minus lambda to the k over k factorial. K is from 1 to infinity. Okay, and you get lambda. For the variance of x, you can use similar arguments. You can get lambda for that. Okay, is that clear? So in a Poisson distribution, the mean and the variance of the random variable are the same. Okay, the mean and the variance are the same. Furthermore, if you have many Poisson random variables and they are independent, then the sum of xi follow the same distribution, the same Poisson distribution. Follow a Poisson distribution with the variance. With the parameter lambda is the sum of the parameter lambda I. Or let's say the mean of xi in this case is lambda I, then we can say that the mean of the sum of xi is the sum of the mean of xi, and you come up with the sum of lambda I, right? And this is the parameter of the Poisson distribution. Okay, you can think about it this way. Suppose that x1 is the number of red cars, x2 is the number of blue cars, and x3 is the number of black cars. Then you can and suppose that they are independent. In reality, they are not really independent. But if we under some situation we assume that they are independent, then we consider the sum of the three x1, x2, x3. That is the number of red, blue, and black cars, right? And the number of red, blue, or black cars is also a Poisson random variable, right? And then you get a Poisson distribution here with the parameter lambda, and lambda is the mean of the sum, and as I said, the sum of the mean, the mean of the sum is the sum of the means, so you get the lambda 1 plus lambda 2 plus lambda 3 for the parameter lambda. All right, and then you get you have these two properties of a Poisson distribution. Actually, in fact, there are some more interesting properties for a Poisson distribution, but I don't think we have enough time for that. So I just introduced these things to you. Next, I want to give you some graphs of Poisson distributions. We have the three distributions here. equals 0.5, when lambda equals 0.5, the distribution is heavily skewed. Okay, when lambda is 5, distribution is still skewed but less skewed than the previous one. All right, and when lambda is 20, the distribution is more symmetric. Am I right? Okay. Okay, let's consider this example. Consider an experiment that consists of counting the number of alpha particles given off in a second interval by 1 gram of radioactive material. If we know from past experience that on average 3.2 such alpha particles are given off, what is a good approximation to the probability that no more than 2 alpha particles will appear? So suppose that X is the number of alpha particles. Given up in 1 second. Then X follows a Poisson distribution with the parameter lambda. In this case, lambda is the mean of X, right? And that is 3.2, okay? Then now you want to find the probability that X is less than or equal to 2. That would be e to the power minus 3.2, 3.2, 0 over 0 factorial for the probability that X equals 0, and then X equals 1, and then X equals 2. Do you understand what I'm saying? Is that all clear, everybody? That makes sense? That makes sense? It's okay, right? May I move on, everybody? Again, all right. Suppose that X is the number of alpha particles given up in 1 second. Then X is the number of events that you can observe during a period of time, 1 second, right? Then we can say that X followed a Poisson distribution with the parameter lambda. And lambda in this case is the mean of X, and that is the average number of alpha particles given up in 1 second. Okay, and that is 3.2. From past experience, we have that number. So you get this one, and then you want to find the probability that X is less than or equal to 2. It is the probability that X equals 1, X equals 2. X equals 0, 1, or 2. Understand? The probability that X equals 0 is the exponential minus 3.2 times 3.2 to 0 over 0 factorial. And you have the other terms. Is that clear? Is that clear? Okay. All right. Is there any other questions, everybody? Let's consider this example. Flaws occur at random along the length of a thin copper wire. Suppose that the number of flaws follows a Poisson distribution with a mean of 2.3 flaws per millimeter. Find the probability of exactly 2 flaws in 1 millimeter of wire. Okay, then in this problem, we need to deal with the number of flaws, right? So let's X be the number of flaws in 1 millimeter of Y. So in question A. And you see that X follows a Poisson distribution with the parameter lambda. In this case, lambda is the mean of X, and that is 2.3 flaws. Okay? Then the probability that X is exactly 2 should be e to the power minus 2.3, then 2.3 squared over 2 factorial. Okay? And you get the answer 0.2651. All right. And this is what you get. Okay. For question B, you want to deal with the number of flaws in 5 millimeter wide. Okay. So let Y be the number of flaws in 5 millimeter wide. Okay. Then Y follows a Poisson distribution with the parameter lambda, where lambda is the mean of Y. In 1 millimeter of wire, you observe 2.3 flaws. In 5 millimeter of wire, you expect 5 times 2.3, and you get 11.5 flaws. Then the probability that Y equals 10 must be exponential minus 11.5, and then 11.5 to the 10 over 10 factorial. Okay? Is that all clear, everybody? Is that okay? Good. So you get something like 11.29%. Okay? Any questions so far, everybody? Now I want to talk about the approximation property. On the screen, you can see 3 distributions, right? The first distribution is a binomial distribution with 2 parameters n 16, p 25%. The second distribution is a Poisson distribution with the parameter lambda 4. The last distribution is another binomial distribution with the 2 parameters 104%. You can check to see that the 3 distributions have the same mean value. They are 4. They are all 4. Okay. And then, you can see that the first distribution and the second distribution, they are completely different. Okay, they are completely different. However, when you compare the second and the third distributions, they are very similar to each other. It's really hard to recognize the difference between them, right? Okay. So what is the point? The point is that in the first case, n is only 16. In the last case, n is 100. So it seems that if n is big enough, a binomial distribution is very close to a Poisson distribution. Do you understand? All right. Okay. Then we come up with the following. We can come up with the following result. We can have a look at the formula over here. When n is greater and greater, let's say n goes to infinity, the Poisson distribution is very close to a binomial distribution. All right, the limit is 1. The ratio of the 2 probability mass functions is 1. So you can approximate a binomial distribution by a Poisson distribution. If lambda equals n times Pn when n goes to infinity, and lambda is a constant. All right, is that all clear, everybody? It should be okay, right? Okay. Let's consider the following example. Suppose that 1 in 5,000 light bulbs are defective. What is the probability that there are at least 3 defective light bulbs in a group of size 10,000? What do you think? Can you get the answer? Okay, it seems that you want to, we can start with this. You get, suppose that X is the number of the effective light bulbs. Okay, and then you get, let's say, among, let's say in the group. The next follows a binomial distribution because you want to check 10,000 bulbs, so you get 10,000 here, and the defective rate is 1/5,000. Okay, then you want to find the probability that X is at least 3, so you get 1 minus the probability that X is less than or equal to 2. Okay, so you come up with 1 minus 10,000 to 0, 1/5,000 to 0, and then 1 minus 1/5,000 to the 10,000. Okay, and then minus 10,000 to 1. This, let me see, to the 1, to first 1 minus this one, to 9,999, and then 10,000 to 2, 1/5,000 square 1 minus 1/5,000 to 9,998. Okay. However, dealing with small or big numbers could be a problem with your calculator. So you may want to think of using an approximation here, because the value n in this case is 10,000. It's quite big, right? Then you can approximate it by using a Poisson distribution, and the parameter lambda is simply the product of the two numbers, right? And you get 10,000 times 1/5,000, so you get this value, which is 2. Lambda is 2. Okay, lambda is 2. Then I can approximate. In fact, I can approximate this probability by 1 minus the exponential minus 2 to 0 over 0 factorial plus 2 to the first over 1 factorial plus 2 squared over 2 factorial. Do you understand? All right. Is that all clear, everybody? Is that all clear? If you use the binomial distribution, this is what you get. If you use binomial distribution, this is the answer you get. Okay. And if you use Poisson distribution, you get a very similar result. Okay. Makes sense? All right, let's consider the next one. Suppose that there are many observations here, and you want to estimate the probability that x is less than or equal to 2. If you have no information about the distribution, then you only need to have a look at the values which are less than or equal to 2. I can find 4 numbers. Then this is simply close to 4 over 10, and you get 40%. Is it okay? You only get 40% of that. But if the distribution is a positive distribution, do you get the same value or different number? Please think about it for a minute and then tell me. Can you get that? Can you get the answer for this problem? Well, in fact, you can estimate the parameter lambda, and lambda in this case is the mean of x, and you can approximate that by the sample mean, right, which is 3 plus 3 plus 2 plus 0, all divided by 10, you get 2.6. Okay, and then you can see that x follows a Poisson distribution with the parameter lambda equals 2.6. Then you can find the probability that x is less than or equal to 2. So you get the exponential minus 2.6, 2.60 over 0 factorial plus 2.61 over 1 factorial plus 2.6 squared over 2 factorial. Okay? And the results you obtain is simply 2.6, so you get about 51.8%. All right. Is there any questions so far, everybody? Any questions so far? Any questions? Okay. Okay, I think that's it. I want to discuss something more, but I think that's enough for today. I don't want to start something new just because we have 5 minutes left. So I just want to give you a review of what we have learned so far today. We have learned, we just finished the previous chapter with some examples of the variance and then the joint distributions, right? And in this chapter, we have learned the binomial distribution and Poisson distributions, okay? And for each distributions, remember that we try to learn the meaning. We need to learn the meaning of the distribution. You need to, so that you know how to use it. And then you want to know the distribution of the distribution of that specific distribution, that one. So let's say you want to know the chance and also the values that the random variable may take. Okay, so you come up with the point math function for this, and then we learn some characteristic. Okay, for example, we talk about the mean, we talk about the variance values. All right. Okay, and then we discuss a little bit about the approximation for Poisson distribution. All right, or let's say the sum of Poisson random variables, independent random variable, Poisson random variables is also a Poisson random variable. Okay, so that is what we learned so far in this chapter. We are going to study uniform distribution, exponential distribution, number distribution, and the central limit theorem next time. Okay, is that all clear? All right, I think that's enough for today. Let's stop here and see you on Wednesday. Okay, goodbye.